Hi there! In this video, we'll learn about one of the most important topics in computer science, big O notation. We will go over the topic from a very high-level perspective just so you understand the story behind it and why we need it. We use big O notation for determining how long an algorithm takes to execute. There are usually various approaches for solving any problems, and big O notation is a way of comparing efficiency of different solutions to a problem. More specifically, big O notation shows how quickly the number of operations grows as the input gets larger. It may sound a little complicated, so let's break it down a little more. How quickly the number of operations grows. As we know, an algorithm is a defined set of operations that solve a problem. It takes an input, processes it, then spits out an output. And the number of procedures needed to compute the output mostly depends on the input. The larger the input, the more time it takes to compute. As the input gets larger, input can get large really fast. When that happens, we want to know how our algorithm handles the pressure. There might be a variety of steps in our algorithm, but we only care about the ones that increase the fastest as the input grows. We cannot measure the speed of an algorithm in seconds because then it would depend on the power of hardware, processors, etc. Difference of power in devices would lead to inaccurate results. So instead, we calculate the speed by measuring the growth of runtime relative to the input, which is big O notation. Let's look at some examples here. The most efficient algorithmic complexity is constant time, or big O of 1. The function here takes a list of items and prints out only the first element, assuming that the list is not empty. There could be any number of items in the list, 1 or 100,000, it still would require only one step to print out the value. Hence, we say that this function's runtime is big O of 1 or constant time. Most common complexity is linear runtime, or big O of n being the input. For example, when a function accepts an array as an argument, iterates through all of the items and prints every single element in it, we say that the function runs in linear time, or big O of n. Another common runtime is quadratic. It usually happens when we have nested loops in our function. Inner and outer loops iterate through the array the same amount of time, which result in big O of n multiplied by n, or big O of n to the power of 2 runtime. Another runtime which we see often is logarithmic runtime. An algorithm is considered to have a complexity of a big O of log n when it consists of a loop, and the loop variable gets divided or multiplied by a constant number. Let's take a look at the example function here. The function sum1 takes two arguments, an input n and a constant number c. While iterating through the list of elements, the for loop index number gets multiplied by the constant number, which forces the loop to skip certain elements. The second function sum2 skips the elements by dividing the index pointer value. When we encounter such algorithms, their complexity is almost always big O of log n. There are a few rules we need to remember when dealing with big O notation. The first one is dropping the constants. When we have a complexity of big O of 2n, we can drop the constant number in runtime and convert it into a big O of n. And it is because big O notation only describes the rate of increase. As the size of the input gets larger and larger, number of operations increase relative to the input, while the constants stay the same. So they are not relevant in identifying the rate of growth. The second rule is ignoring non-dominant terms. We should also drop the non-dominant term values because when defining the worst case scenario, for example for big O of 2n plus n cubed plus 74, the small factors such as plus 74 and 2n become unimportant. So we can reduce the original runtime to just n cubed in order to focus on what actually matters. Another rule to remember is related to recursion. Recursive code can be a little tricky to analyze. Most common way of computing the big O of recursive function is to visualize it as a tree and determine the depth of the tree and the number of branches on each recursive call. Then we could define it as big O of branches to the power of depth. For example, let's say we have a function that calculates the first n Fibonacci numbers. We could define the complexity of this function by applying a random value. We already know from our function that there are two branches getting created on each recursive call. When we send the number 5 as the input, we can see that the complexity of the algorithm is big O of 2 to the power of 5. It shows that the runtime of recursive function is usually, but not always, equal to big O of branches to the power of depth.